Okay, so last lecture we were talking about random variables, which basically take us from a sample space of events and maps us to some number, right? And that number we can provide with some sort of probability measure. And so we sort of discussed, this idea of discrete random variables and continuous random variables. And, in some ways it's very similar to what we were doing before, except the distinction here is that probability is not necessarily distributed evenly. We're going to have a lot of cases where probability is distributed unevenly, and we want to sort of account for the different, account for that in the questions that we ask. And so, some of this is sort of, in some ways, a repetition of what we were seeing in chapter 2, but instead of, the distinction here is that instead of dealing with statistics, we're dealing statistics that you sample, right? We're dealing with probabilities of some sort of population, okay? So we're sort of working in the other direction where you had some population, right? And here you had some sort of sample. So now we're looking at a different side of it. Usually in the sampled case, we are saying what's the average, right? Or what's the variance of the sampled data. In this case, we're going to be talking about the average of the population or the variance of the population or the random variable associated with the population. So that's sort of the distinction here. So again, a lot of these ideas should be pretty similar to what we've already seen. Like there's one of those little black bugs that are paired up. Okay. So let's sort of do an example. Usually when we're doing these problems, at some level we are dictating distributions, okay? And that's where things get a little bit different. And so you can do a little example problem. Let's say I have a cyber cafe with 6 computers. And what's going to happen is we're going to define this variable x, and it's going to be the number of computers in use, let's say at 12 p.m. All right, so we can be very specific. And what I'm going to say is, well, the number of computers x in use, and this little x in this case goes from 0 to 6. Oops. And what I'm going to tell you is that the probability of any value of x has a specific value. Okay? So again, this is a little bit different from sampling where I say, hey, if I look over 365 days out of the year, right, at noon, what fraction of those days did we see 0 people at the computer? Okay. In one case, I'm sampling and I'm gathering data. In this other case, I'm sort of dictating, right? I'm telling you, this is the probability. At some level, these lines kind of blur a little bit because usually we use statistics to infer these probabilities, right? So there's certainly a relationship there. And again, that sort of is the loop, right, between the population and the sample. Okay, so let's say we had these different probabilities. And I'll sort of draw some lines to make it a bit clearer. Okay. So one question that we might ask is, what's the probability that at most 2 computers are used? Okay. So if we're going to say at most 2 computers are in use, then what we're talking about is the probability that this random variable x, okay, is less than or equal to 2. Now we can write that as, if we wanted, now this is, we should understand this sort of a compound event. And we can relate it back to simple events, right? That's just given by the probability that x is equal to 0, plus the probability that x is equal to 1, plus the probability that x is equal to 2. So what allows me to actually break up this compound event into simple events?
The fact that it's a discrete variable?
It's discrete, but there's some, yes. So you're giving me the higher order, which is exactly right, but there's a specific property.
They're mutually exclusive.
Yeah, mutually exclusive. So we know our discrete variables will be mutually exclusive, right? But this mutually exclusive and exclusivity allows us to break apart this compound event. So from there, we can just sort of add up these probabilities, right? So this is the probability of 0 plus the probability of 1 if we want to use different notation, right? And so we can just fill it in. So check, I don't know what that is, 0.3, okay? So the probability that x, our random variable, is less than or equal to 2 is equal to 0.3. Okay. Now, when we talk about these probabilities, right, both here and here, it's, I like the idea of sort of defining exactly what we mean. We kind of did some of it here, right, up above, but let's go ahead and give a little bit more of a formal definition. All right. And specifically, we want to talk about probability distribution functions, okay? So you'll see me refer to it as a PDF, right? The probability distribution function Okay, so this is a bit verbose, right? But essentially what we're saying here is that we are going to have these probabilities that we calculated or we used up above. So this stuff right here is in fact something special, and it's called a PDF, or probability distribution function. And it explicitly tells us how probability is distributed over the whole sample space. Okay? Now again, because random variables are a little bit weird, they can map non-numerical values to numerical values. But if you just want to think about it as, hey, we can give a specific probability to any outcome or to any specific value of random variable, that's fine, okay? But again, it's how probability is spread about over all the values. Now, as we sort of mentioned, we still have to follow the axioms and properties of probability. And as a consequence, we have two specific properties that we need to maintain, which is the probability of any value of x, right, has to be greater than or equal to 0. And that's for all x in the range of x, right? So x is some function, right? So all the values that our random variable x can take on, the associated probability has to be greater than 0. Okay, it's fine. So no negative values, right? More so, we can say that the sum of those probabilities has to equal 1. You'll see this quite a bit in math where they're not explicitly clear what they're summing over. They're just saying, hey, we're going to sum over the variable x. And the assumption is that you kind of know what are the values that x can take on, okay? So in this case, x corresponds to the range or all the values that the random variable x can take on, right? So later on, we'll be a little bit more specific, and you might see us, we'll write something like x in some d, right? In some domain or some range. And we'll write something like that, right? But just be aware, sometimes you'll see this. I don't particularly like doing that because I think it's a bit sloppy. I would suggest you not try to do it as you move forward in your mathematical pursuits, especially in engineering. It's always a better idea to be more explicit, right? So, but I don't know. Okay, so what we often see, so if we go back to this example problem, is we often see PDFs represented pictorially. Okay. And so for this prior example, we had a different number of computers throughout the day. So we had 0, 1, 2, 3, 4, 5, and 6. And we're going to represent the probability of them being used, right? So I think we had something that sort of looked like this. Okay. Now, the important part here, or at least I find it important, and I sort of mentioned it, is this is concentrated probability. And it's represented with a delta Dirac function. Right? So if you've ever seen that notation in your physics classes, or if you're in electrical engineering, you'll certainly see it. Again, all our probability is concentrated at a single value, right? Because we sort of used the example where I said, what's the probability you're 5'8"? And I know you're nowhere near that, right? But the idea is, he's not, even if he was around 5'8", he certainly is not exactly 5'8", right? And so with continuous variables, we can't do that. But with discrete variables, we can. We can concentrate, and we do concentrate probability at a specific number, right? And this is because we can't have 2.37 persons in a cyber cafe, right? It has to be a whole number. Okay. Certainly, we can talk about other probability functions. Let's say UCF wins the football game. Right. And this is one that or a type that we're going to see all the time. Here, the sample space is given by sort of win and lose. Okay. And what we're going to say is our random variable, x, can take on two values. One if we win, all right, and if we lose, it's going to take on a value of 0. We can assign a probability for each of these to happen, right? So normally we say, I don't know, the probability of winning is something like 95%, and the probability of losing is 0.05. Okay. And so you'll see it as the probability of 1 equals 0.95, and the probability of 0 equals 0.05. Okay. And of course, this is sort of the idea of saying the probability that we win. Right. Okay. All right. So this is actually a very common distribution that we're going to be working with. And I don't know, did I mention Bernoulli's last time? Yeah, okay, good. I don't remember anymore. Okay, so there's something called the Bernoulli distribution. Okay. And it's going to be parameterized by a single value p. Okay, so in this case, p is equal to 0.95. Okay, and this sort of leads us into our next sort of discussion, which has to do with family of distributions. What ends up happening is that we start to see the same distributions over and over and over and over again in science and mathematics and in engineering. And so it makes sense to represent them analytically where possible. Okay, so a few examples might be, I don't know, what's the average weight of newborn babies? All right. How long until the next customer? All right. Another one might be service time at a cashier. Okay. It ends up that the things we care about the most, we've actually done a lot of study to understand how do we provide a mathematical model for these things, right? And so the ones you probably hear about the most are the normal distribution, right, or the bell curve, right, where it's defined by two parameters, sigma and mu. Okay. The other one that we just defined is a Bernoulli variable, right? So we'll have some probability of 0 and some probability of 1. Some other really common ones, and I'm going to do my best to draw it, but I'll probably do it badly. So this is a Poisson distribution. Poisson is commonly used for things like how many phone calls do I expect to get in the next hour? Okay. This type of problem was actually really, really important at the dawn of the telecommunications industry, right? So when we first invented telephones, what needed to be invented with it was a switchboard, okay? Where somebody manually, you'd pick up your phone and you say, hey, I want to call Will, and the operator would listen, and he'd sort of short circuit the wire that is going from your house to the center operator. They'd wrap a wire around to Will's telephone line, plug it in, and then that would call Will. And then you guys could speak to each other, right? So one of the big questions was, how many telephone operators do we need in a city, right? How many people do we need to hire? And that was based on how many phone calls they would get per unit time. And they'd represent it with a Poisson distribution. And so this Poisson distribution is really important to something called queuing theory, all right? So queuing as in lines, right? So here it was just lines for, people waiting for the operator. This was very important in sort of, call centers, right? They really care about queuing theory. One of the people who surprised me cared the most about queuing theory is the IRS. Does anybody know why the IRS cares about queuing theory with their call centers? What's the goal of the IRS? Not to get you to hang up. In fact, quite the opposite. What's the goal of the IRS? What's their function? To get your money, right? If you don't understand your taxes, you're not going to fill them out, okay? And the government's not going to get their money. And so one of the things that the IRS invested in is to actually, relative to the government, have the most efficient call centers, okay? Because they want your money. They realize that for every customer service operator they put into play, the more money they get back, okay? Now, every other function of the government doesn't work the same, right? Every customer service representative they put at, I don't know, pick another agency, right? The FBI doesn't really help them, right? It's just costs money. But the IRS is the one where they make money for each customer service representative, right? So they were very big into queuing theory and understanding how it could be used. Okay, but the main premise is we have all these descriptions of random variables, and we can model them using standard specific equations, okay? Now, we're going to start by learning about families of distributions for a few specific discrete random variables. Okay. And so we've kind of learned one, which was the Bernoullis. All right. So we learned the single event one, but there's also a Bernoulli experiment or trials. What are the other ones? There's a whole bunch of other ones. Another one is Poisson. Okay, and again, this had to do with like, how many arrivals do I expect per unit time? That's another good one. I want to give them an, oh yeah, there we go. So we have hypergeometric, and the other one we're going to talk about is a negative binomial. Okay. These types of random variables come up so often that we've started to develop a notation on how to refer to them. Okay. So for the Bernoulli equation, or Bernoulli random variables, we'll say something like x has the probability distribution of a Bernoulli defined by some parameter p. Likewise, we'll see the same. If we're doing a Poisson, we might write. So some people will shorthand it as Pois, right? Some other people will write out the whole thing. Right? All depends on who you are. And Poissons get parameterized usually by a lambda. Alternatively, you might, I think the book uses Poisson mu, but same idea. Okay. Lambda is usually used as an arrival rate, okay, when we're doing queuing theory. All right, so how many phone calls or how many customers do we process or get per unit time? Well, mu is usually considered a service rate. So if you're working at McDonald's, how many customers do you get per hour is lambda, but mu is like how quickly can you process them at the cash register. Okay. So normally lambda is an arrival rate. While mu is a service rate. Okay. So these are two things that are very important. Now, with each one of the, there's one more we'll do. Oh, it's kind of a specific example of this, but we'll have a geometric as well. So we'll actually do an example of a geometric because I think it's sort of a fun one. So let's say me and my wife or partner are trying to have kids, and I've always wanted a little girl, so we're going to keep having babies till we have a little girl. Okay, we're going to do our job for America. All right. So the question, or what I'm going to do is I'm going to define a random variable x, right, which will be the number of births until a girl is born. Okay. Now this is sort of a fun problem because I think it takes Bernoulli's to another level, and it sort of sets the stage for a bunch of other stuff. Okay, so we have our random variable, or at least we've defined it. And so we can think of our sample space, right? We can have a few different things, right? I could have a girl right away, so that's one option. Another option is I have a boy and then a girl, and then, or a boy, boy, girl, boy, 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 girl, and so on. All right. All right. And so this idea is that our random variable maps each element in our sample space to a value. It keeps going on. Now, let's assume that the probability of a girl of having a girl for any particular child, we're going to assume it's equal to 0.1 or 5.1. Why not? But more broadly, we'll keep it as the variable p for now. And we're going to assume that it's independent for each child. It's actually interesting to note that the probability of having a boy or girl is in fact somewhat influenced by our environment. I forget what it was. I think one study showed that during times of war and stress, the proportion of girls born actually goes up, which is really, really neat. They've noticed the same phenomenon in deer and other animals, which is kind of cool. I don't know. Yeah, it's pretty neat. Some people try to do some like evolutionary biology with it, right? To sort of explain what's going on. But I thought that was really, really neat. Okay, and I know there are some cases where it's actually quite dramatic. Oh, I learned this at Gatorland. You can control the sex of the crocodiles by changing the temperature of the eggs. And in fact, you can make it like all male or all female, or almost all male or almost all female. It's like incredible. So I thought that was really neat. I don't know. Okay. Okay, but that's actually after insemination, I think. I don't know. So we don't have biologists in this class, do we? No, okay. Somebody takes biology. Ask that question. How do they do that? Okay. So we can start calculating the probability of all these events. Okay, so I can calculate what's the probability of just having a girl right away. It's given by P. What's the probability of having a girl after a boy? It's 1 minus P followed by P. We can do the same thing for 3. All right, so we have 2 boys and then a girl, right? So again, we're having boy, boy, girl. And so we're multiplying the independent probabilities using what we learned in the previous lecture. So here we have 1 minus P times 1 minus P times P. Okay. And this sort of repeats for any number of births until a girl. And so this is actually called the geometric distribution. And it's just parameterized by P. Okay. Of course, this applies to all sorts of problems. How many games until... Yes, ma'am. Yes, K minus 1. Thank you. Yeah. And in fact, we can write the shorthand notation for this. Oops. So usually it's easier to write it as a function. And so usually we'll see discrete probability distributions written something like this, right? So the probability of any x is given by an equation, and we define what x that equation is valid for. And then we say all other values of x are equal to 0. Okay, and that sort of jives with what we already saw up here. Right? Oh, well, we can say right here as well. Right? All our probability is concentrated in these areas. Okay? Here there's nothing less than 0, and there's certainly nothing in between those values. Thank you for the correction. Can you remind me of your name? I know your name. Hyacinth. Yeah, it's got 3 vowels in a row, right?
Oh yeah, AI.
Yeah. Okay, that's how I remember you. Okay. Okay, so these types of distributions come up all over the place, these geometric ones. Okay. Now, again, this is a PDF. Okay. So a lot of you are used to looking at PDFs, at least graphically. Histograms are kind of like closely related to a PDF, or these frequency diagrams we did are closely related to a PDF. In a lot of the work that I do, I'm actually more interested in cumulative distribution functions. Okay. And informally, we can think of CDFs as just the integral of a PDF. But when you're working in the discrete world, it means a summation. Okay. So the cumulative distribution function, and we'll call it a CDF for shorthand. And we'll denote it as capital F of x. Right? So this cumulative distribution function denoted f of x. And let me be clear here, this is a small x. All right, so I'm just sort of exaggerating the tininess of it. For a discrete random variable big X with PDF p of x, right? So it's going to be defined for every x, and again, this is a little x, by the following. So f of x is going to be equal to the probability that a random variable is less than some value x. Okay. We can write that using the summation, where we can say it's the sum over y, where y is less than or equal to x, and I'm going to use some funny notation. I'm going to be a little bit hyper-specific here. It's the sum of the probability of y. Okay. So this thing that I drew here, let's sort of talk about what that is, because I think this is a little bit interesting. This is a round down function. Okay. If I wanted to round up, I would actually write it like this. Okay. So the reason why I write this round down function is because what if I said I want to calculate the probability that x, the number of children I have before a girl, is 3.5. Well, that doesn't really make sense. So what I do is I actually round down to 3. Yeah. Okay. So another way that this gets denoted, so just be aware of it, is sometimes you'll see the random variable explicitly stated. Right there. Again, this is sort of really useful if you're working with multiple random variables. So let's say, and I think I talked about this, let's say we're rolling 2 dice. All right, and this is rolling dice 1, and this is rolling dice 2. Okay. In that case, we can talk about the distribution, the cumulative distribution of y, and we can talk about the cumulative distribution of x. And we're sort of clear about which one we're talking about. And of course, we can talk about the cumulative distribution of z. Okay. So that's why, if you have multiple cumulative distributions and you're doing funny things with them, it's sort of helpful to maintain good notation. Now, unfortunately, I don't have the opportunity to grade you on notation, which is sort of a pet peeve of mine, because I'm very hyper aware of it. Okay. CDFs are really useful because they kind of jump to the point, right? In this problem, yeah, I can give you the PDFs. I can say, what's the probability I have 2 boys before a girl? Okay, so if we were to do that, it would just be 1 minus p squared times p. And we can do that on our calculator. So it would be 0.49 times 0.49 times 0.51. So it would be a 12 point, something like that, 0.122 probability that I have 2 boys before a girl. Okay, so my partner might not like that idea because that doesn't really mean much to her. She might go, well, I don't want to, like, you're telling me the probability of having a girl by the first, second, or third. I want to know what's the probability to have a girl within 3 children, right? That's probably more likely how she would think about it, and I certainly don't blame her, right? And so in that sense, a CDF is a lot more helpful, right? Because we can take that probability distribution and we can ask, what's the probability of having a girl within, let's say, 4 children? So in this case, what we're talking about is if we go back to this geometric distribution, we're talking about calculating what is our cumulative distribution, f of big X, less than 4. So we can actually work this out. Okay, so we can go to Excel. And what we're going to do is we're going to do this summation. Right? Now in this case, we're going to be summing x equals 1 to 4. Okay? But maybe we want to know it for any arbitrary x. Okay? And so if we're looking for this value, right, for any arbitrary x, this is our CDF. All right, so let's sort of see the difference between these two guys. So I'm going to say p equals 0.51. And what I'll do is I'm going to calculate the probability of x, and then I'll calculate the CDF of x. And so we'll go down to 20 children. Hopefully that doesn't happen. All right. And so we can just implement our equation here. All right, so in this case, we are going to set it equal to 1 minus p, and p is this 0.51, and I'm going to use the dollar sign just so I can apply this equation downward. So I'm just applying the equation we already had. Oops. Times b times 1. Okay, so if I did this right, nope, what did I do wrong? Oh, did I do something wrong?
You had 2 asterisks.
Oh, I did? Okay, so I just corrected it. Okay, so 0.51. All right, that seems right. Because the probability of having a girl at any time is 0.51. And I can fill this down, and that will give me my probability distribution. Okay, so sure, great. This cumulative distribution function is basically the integral of p of x, or the running sum. Okay, so what I'm going to do is I'll just sum from this first value until itself, but I'm always going to hold this first value constant. So when I go to the down one row, the CDF is adding this value and this value together, right? So if you see 0.51 plus 0.2499, I get about 0.76. If I add another 12%, right, or 13%, whatever it is, 12%, I get about 88, right? And I can fill this down. Okay, so let's sort of see what these look like. So first I'll do this plot, and I'm going to try to be technically accurate. Let's see if I can actually do that. Do they have stem charts in Excel? I don't think they do. Not line, not bar. Okay, so technically this will be kind of wrong, but I'm going to do it anyways. Okay, so this is the PDF that we see here. Okay. This is our PDF of the probability of having a girl after X number of children. Right? And actually, I don't like this because this is in fact wrong. Actually, no, it's right. I take it back. Sorry, it's right. Okay. So it starts at 1, so I'm happy there, and we start at 0.51. Okay, so let's see what our CDF looks like. So I'm going to highlight these two columns. Oops. Yeah, there we go. So some of this is technically correct and incorrect. In fact, this is incorrect. Okay, and I'll tell you why in about a second. So in fact, what I'm going to do is I'm going to get rid of these lines. Let's see, change chart type. Okay, so if we want to be technically correct, let's see, I don't have my pen. Can I draw on these things? Let's cross our fingers. Ooh. Remember, our PDFs have these delta Dirac functions. Okay, so this should be like a stem chart. Now, for these CDFs, right, so this is our CDF function. It actually looks a little bit different. When you're working with discrete data, you're actually doing a zero order hold, okay? So what's the probability I have 0.5 children before I get a girl? 0. Yeah. So what we do is imagine this is an open circle. Let's see if we can zoom in. Yeah, there we go. So our function is actually an open circle until 1, and then it's a closed circle from 1 until 2, and then it's open, closed, open, kind of like this. Okay, and then it sort of bleeds in, right? You can't really distinguish the open and closed anymore, but they're there. Okay. And so this is technically the correct CDF for a discrete distribution. Right? And these flat lines, again, the reason why they're flat is because you can't have like half a child. It just doesn't make sense, right? Our probability is concentrated in these peaks, right? So if I ask what's the probability of x less than 2.5, well, we just go to x equals 2. We go right here. Okay? It's constant along that little segment. Okay. So that's just something to be aware of. Okay. All right. So we can actually calculate this. So, I always like a little bit of math in the afternoon. So let's actually calculate. You want to calculate that? No, let's do this. So we can actually come up with an analytical equation for f of x. Okay? And again, we know it's equal to the sum of y less than x rounded down for our probability of y. Okay? And again, you know, so this is kind of why we put the random variable here. So we're summing over some variable y that's less than x. All right. And so you can see that one reason why it's good to put the random variable in your CDF and your PDF, right, or your probability, is because the value that you might be substituting inside of the function might not be x, right? So, because in fact, we're saying we want to know the probability that x, the random variable, is less than some specific value x, all right? And all those values that are smaller than x are going to be this y. Okay, so this gives you some intuition why we like to put this value here. Okay, so again, we already have what this probability distribution function looks like. Okay, so I can be a little bit more formal and start filling it in. What's that guy? Because we're summing over y, we can actually pull out this p. And we can do one other little trick, which is we can change the bounds, okay? So instead of going from 1 to the round down of x, we can go from y equals 0 to x minus 1, and what we're going to do is we're going to shift our power. Right? So we're basically doing a substitution. Or you can think, another way you can think about it is we're letting, I don't know, z equals y minus 1. Right? And then we're saying z equals 0 to whatever that is. That's fine. Okay. Okay. So what you'll find in probability is that all these things, you guys have taken Calc 2? Yeah, so you remember your series and sequences? All right, probabilities is just series and sequences hell, okay? Or not hell, I enjoy it, so I think it's fun. Okay, so the reason why this is called a geometric distribution is because this is actually a geometric sum. Okay, so I never remembered these things when I was at your age. So I'll just give you the answer. And hopefully with time you'll learn to appreciate these different series, especially geometric series. Now this isn't an infinite series. It's a, what is it called?
Convergent.
No. When you stop it. Not compacted, but truncated series. There we go. Okay, we're not actually summing up to infinity. We're summing up to some finite number. All right. And so a geometric series of the following form is given by the following equation. Okay, so in this case, our A is equal to 1 minus P. Okay, so in our problem. All right, so that lets us sort of fill things in. And our K is the round down of x, right? X rounded down minus 1. So this guy and that guy are the same. Okay. So we can apply this equation right here, and hopefully I did it right. Yeah. Okay, so clearly we're going to have a bunch of cancellations here. So 1 and 1, they cancel out. They'll also cancel out these guys here. So what are we left with? Ooh, we're going to have even more. So we're left with another cancellation. All right, so this is our CDF function for a geometric distribution parameterized by P. All right, so we can actually see whether it works or not. Why not? We'll go back to our Excel spreadsheet. And so this is the analytical equation. All right, so I'm going to say it's equal to 1 minus, where did I put P? There we go. I'll hold that guy constant. And we're going to take it up to the floor. So floor just means round down. It's another way of saying round down. Oh, too few arguments. Oh, 0? What is, oh, wrong one. Surprised it makes me do that. No? 1? Let's see. Ooh. Crossing my fingers, I know how to use floor. Ah! There we go. Okay, good. And so what we see is that these equations, in fact, do match, right? So it's always good news. Okay, so you can see how going from a PDF that is defined by an analytical equation, right, we could calculate the CDF and provide an analytical equation. And again, what I mean by the analytical equation is this guy right here. And so this is going to be really common with families of distributions, right? So we're going to be able to write down equations for the PDF and the CDF. Now the CDF is really, really useful, right? Because it has one of the following properties, right? So for any two numbers, A less than B. Actually, we can say less than or equal to B. Okay. The probability that a random variable x is between A and B is equal to the CDF of B minus A minus. Okay. What's this A minus mean? So this was actually a new one to me, right? So A minus, it's the largest integer value that's smaller than A. Okay, so if I say 5 minus, then that's equal to 4. All right, if I say 3.5 minus, that's equal to 3. Okay? So it's like a round down, but it's even harder, right? So this 5 minus gets rounded down to 4 in a way, right? So it's the next largest integer. So this becomes useful, right? So we can go back to me wanting to have children. So you'll think I'm baby obsessed at this point. And so we can ask the question, what's the probability I have a girl between 2 to 4 children? So oops. Alright. So again, we're calculating this guy. And I will try to be very careful about drawing my capital X's, my random variables, with these little script thingies. If I ever draw something that is confusing, ask me, is that a random variable or is that an instance? Okay. And I will try to be careful. Okay. So based on the equation above, right, it's just equal to, well, we can work through the steps. It's the probability that x is less than 4 minus the probability that x is less than or equal to 2 minus, right? Which is the same thing as the following using the CDF, so that this equation up here. It's the same thing. Okay. Actually, I should have probably written this in the other order. Okay. So when we write that, in fact, what we're going to calculate is our CDF for 1, right? Because it's the next largest integer value, or possible option, than 2. Okay. So when we do that, we could do one of two things. We could plug in the value of x here, right, which is certainly possible. Or what we can do is reference back to our Excel spreadsheet. And so I can look at what we have here. 0.94 and 0.51. 0.94, 0.51. 0.94 minus 0.51. That's about 0.43. Okay. These notes are wrong, so if you download them online, there's a mistake right there. Okay. Okay, so these CDFs are really useful because they allow you to calculate the probability of compound events really, really quickly, especially if you're trying to figure out ranges. What's the probability that x is between two values? All right, you don't need to sum up all the values in between. All right, so if the question was, what's the probability x is between 1 and 500, I don't need to add up 1, 2, 3, 4, 5, 6, 7, 8, 500 numbers. Instead, all I have to do is look up two numbers, right? The CDF for f equals 500, right? And the CDF for f equals 0 in this particular case, corresponding to the 1. And then I subtract those two numbers. Right? And so that's what makes this proposition so useful, right? And this is what makes CDFs really useful. When we start getting to continuous distributions, CDFs become even more useful because it's really easy to pick out what is the average, the median, the standard deviation, where is data concentrated. If you read CDFs a lot, they're actually more informative than PDFs. Okay. All right, cool. All right. Okay, so before we start talking about these other distributions I promised you we were going to talk about, which was the hypergeometric, the negative binomial, and the Poisson, we're going to talk about two things. One is how do we calculate the expected value and the variance of random variables. Again, this should be very reminiscent of what we are talking about in statistics, right? So they should remind you of each other. Okay, so we're going to start off with the definition, okay, of what the expected variable or expected value is. And we're going to do this for a discrete random variable in particular. Okay, so what I'm going to start off with is we have some random variable, it's a discrete random variable x. All right, the values that that random variable can take on are in some set D. So D could be 1, 2, 3, 4, 5, 6, right? Or maybe it's 0, 1, right? All depending on what our random variable is. And along with that random variable, we have a probability distribution function. Okay. We're going to say the expected value of x, and we're going to denote that as E, this expectation, and usually you see folks use square brackets, so just be aware of that. Sometimes you'll see me use parentheses, which sort of indicates that expectation is a function, right? But the book uses brackets. I sort of go back and forth between the two. But usually the brackets make it a little bit more clear of what's going on. So you can denote it as this expectation of x, or you can write it as mu of x, okay? And remember, whenever we see mu, we should think about population statistics, right? So if we are talking about a sample average, then we'd use x bar, right? But if we're talking about the population and probability, then we're going to use mu. Okay. So the expectation of a random variable is calculated by the weighting of x times the probability. All right. So when we assumed probability was distributed evenly, let's say we had 10 numbers, right? Then, so before, I'm going to put this off to a side. So before we assumed probability was distributed evenly. So let's say if we had 10 numbers where x was equal to 1, 2, all the way up to 10, then p of x was equal to 1/10, right? So if I wanted to know what the average was, I would add 1 plus 2 plus 3 plus ... all the way to 10, and I'm summing over 10, okay? That's actually the same thing as saying 1 times 1/10 plus 2 times 1/10 plus 10 times 1/10, okay? It's assuming that the probability of our samples are evenly distributed. Now what we're saying is, well, that probability might not be evenly distributed, and we need to account for that, okay? And this expected value, I mean, you can think of it as sort of like the average or the mean or something like that, but it's the average or mean for a random variable, okay, where probability is distributed unevenly. Okay. So we'll do a quick example. So let's say I was studying the number of courses a student takes each semester. And this is my probability distribution. Okay. And in fact, we're going to define x this way. And so we can ask ourselves, what's the expectation of x? And we can just apply our equation. So I'll just write out the form of the equation. Now our domain, or our set D that we have, is from 1 to 7 integer values, right? And so we can start substituting in. So we're going to do 1 times 0.01 plus 2 times 0.03 plus 3 times 0.13 all the way to 7 times 0.07. Okay. And so what we're going to get back, if we do that calculation, is 4.57 courses. Okay. So that is going to be the expected value of x. Now, before we leave, I just want to make one point. Do not round, okay? When we're asking for the expected value, even though the expected value does not lie within the set of values that we can take on, this is still the correct answer, okay? Don't give me 4, don't give me 5, all right? Anybody who tells you to round is wrong, all right? There will be cases, especially for those of you who are engineers, where they'll say, what is the, I don't know, the value that minimizes something, right? Value that minimizes the cost to your company. And they'll say, well, you calculate the expectation, and whatever this expectation is the minimizer. Okay, that might be true, and you might say 4 minimizes the cost, but certainly never say that the expected value is 4. Okay, don't round. Right? This is a mathematical, based on a mathematical definition. Okay, so thanks guys. Cool.